Welcome everyone. In this video we are exploring exponential functions, some of the most useful functions in math. They appear in many settings and are useful for describing diverse phenomena such as the spread of epidemics, the increase in computing power, how money accrues, and dating historical artifacts. We'll start with an infamous investment scheme created in 1920 by Charles Ponzi, who lent his name to a whole class of cons. Ponzi proposed to pump his investors' money in a risk-free gambit involving stamps, and promised a return of 50% every 45 days. His company started in January 1920 with an initial investment of $1,800. Ponzi never could make any real money with stamps, and had to use the money from new clients to pay off the old ones. By mid-August he was arrested, having defrauded his investors of about $250 million in today's money. Say we are looking at two investors in Ponzi's scheme. Investor A decides to give Ponzi $100 every 45 days, while Investor B gives Ponzi $100 at the beginning and tells him to reinvest the whole sum every month and a half. Let's see what would happen with the two investments over time if Ponzi's scheme keeps working. First, A invests $100 every time, and therefore each of these investments produces a profit of $50. Constant profit of $50 every period of 45 days amounts to a linear increase. After one period, A has $150, after two periods, $200, after three periods, $250. And we can guess the pattern. After T periods, A has a total of 100 plus 50 times T dollars. What about the second investor? B invests $100 at the beginning, making a profit of 100 times $0.05, but then rather than reinvesting only $100 the second time, B reinvests the total amount of $150. This is 100 times $1.5, which is a convenient way to keep track of the balance. At the end of the second period, B will have made a profit of 100 times 1.5 times $0.5, which is added to the total balance, now standing at 100 times 1.5 squared dollars. The whole amount gets reinvested, and the profit on that at the end of the third period is $100 times 1.5 squared times 0.5, and this is added to the pot. A pattern emerges, but unlike the account of A, whose balance was linear, we see that the account of B grows as $100 times 1.5 to the power t after t periods. Here we have the periods 1, 2, 3, and the corresponding exponents 1, 2, 3. We begin to see a pattern on the balance in the two investments. The balance of A of t, is 100 plus 50 times t, where t is the number of 45-day periods. Whereas the balance of B of t is equal to 100 times 1.5 to the t. The first investment is a linear function, the second is an exponential function. How long could this have kept on going? After all, most investors reinvested all their winnings. What would happen after 1 year? Investor B would have 100 times 1.5 to the 8, which is roughly $2,500. After 2 years, about $65,000, and after 3 years, around $1.7 million. Clearly, this can't work. Exponential functions don't only show up in banking, but also in computer science, in applied math, physics, chemistry, and even baking. So what is an exponential function? It is a function of the type f of t is equal to a times b to the power t. Here a is the initial value of the function, and b is the base of the exponential, always bigger than 0, which can be thought of as b is equal to 1 plus the percent rate of change per period. We've all gotten accustomed to looking at graphs of exponential functions in the early days of the COVID pandemic. It is worth noting the difference in the behavior of exponential functions depending on b. When the base of the exponential function is bigger than 1, in other words, the percentage rate of change is positive, the function keeps increasing. It goes to infinity as the value of the variable goes to infinity, and has a horizontal asymptote at y is equal to 0 at negative infinity. When the base is less than 1, in other words, the percentage rate of change is negative, the function is going to decrease towards 0 as the variable goes to infinity. When the base is bigger than 1, not only do exponential functions grow with increasing speed, they grow much faster than any linear function, even if we might have to wait for a while before we can see this. For example, the exponential function 1.01 to the x is smaller than the linear function x plus 1 until around 700 when it takes it over. Let's see an example where an exponential function decays. About 40 miles from Notre Dame is a nuclear power plant where uranium-235 is used to heat water and produce electricity. Why uranium-235 and not one of its other isotopes, for example, uranium-242? The reason is uranium-242 decays at roughly 4% every minute. A rate of change of negative 4% means that the percentage of the uranium-242 remaining after t minutes is U of t is equal to 100% times 1 minus 0.04 to the power t, which is 100% times 0.96 to the power t. After an hour, we are at U of 60, it's 100% times 0.96 to the power 60, it's roughly 8.64%. Uranium-242 decays so fast that after 24 hours, essentially it is all gone. Exponential functions are ubiquitous in describing real-world phenomena. Now that we've seen a few examples, we can begin to think about their more general uses and properties.